once again here in the Intel Booth Theater during Supercomputing 2024 here in Atlanta, Georgia. We're so glad to have you here. Throughout the day, we're going to be having presentations from our partners who will show how Intel can partner with you to achieve your goals through a multitude of applications. And here's yet another presentation happening right now. It is entitled How the oneAPI library Ginkgo brings scientific simulations to Intel data center GPUs. Here to take care of this presentation is Hartwig Anzt.
Thank you very much for having me here. It's a pleasure to be here. And I'm going to talk about Ginkgo and what we did in Ginkgo to be part of the oneAPI ecosystem and how we can now enable simulations on any oneAPI supporting hardware. Let me start with Ginkgo. Ginkgo is a math library that was initially designed as part of the US XSK computing project. And from the beginning on, we knew that we have to support hardware from different vendors. We knew from the beginning on that we need a reference backend to check the functionality. We knew that we need a sophisticated software development process, and we implemented all of that. We were successful during the ECP, the US XSK computing project, and afterwards the question was, what comes next? And our decision was to move into the oneAPI ecosystem and actually provide Ginkgo as a oneAPI software tool for anyone who is interested in using it on the oneAPI hardware. So Ginkgo provides a set of iterative solvers, a set of preconditioners, a set of batched functionality, algebraic multigrid, and a couple of utility functions. And that's basically the tool set that you need for running simulations, particular fluid flow simulations on HPC systems. The functionality that we developed is scaling very well on Intel hardware. So what you see here is the weak scalability of SPMV for a 27-point stencil matrix and a 5-point stencil matrix on the Intel data center GPU Max series 1550. And you see here the number of tiles. So we see that up to, this is about 1,000 tiles. We see that weak scalability is very, very good. It's not as strong for the 5-point stencil, and that is also expected because 5-point stencil just has lower arithmetic intensity, so the data transfers are more expensive. And on any hardware, you would get lower performance with a 5-point stencil compared to a 27-point stencil. 27-point stencil is also interesting because it's the central building block of the HPCG benchmark. How we can use this functionality for fluid flow simulations, I show that here with taking OpenFOAM as an example. OpenFOAM is a software stack that is used in lot in industry. It's a finite volume scheme that is used to simulate all kinds of fluid flow simulations, from wind turbines over car manufacturing, spacecraft, everything can be done by the OpenFOAM. And what we did is we basically plugged in as the numeric backend into OpenFOAM, and that enabled OpenFOAM to run on any of the hardware that is part of the oneAPI ecosystem. What you see here is that we can run both on Intel GPUs as well as on Intel CPUs. So here you see scalability, you see linear scaling and the speed up that we get in reality for an OpenFOAM application running on up to 128 cores, 128 threads on a 52-core Intel CPU Max 9470C. So there's a Sapphire Rapids. And on the right-hand side, you see the scalability on the data center GPU. And you see the scalability on the GPU is actually much better. And that is because it provides higher bandwidth, scales better. Down here, you see the speed up. Not surprising, the GPU is faster than the CPU. That is kind of expected. We also looked at very different flow simulations. And what we are looking here is a combustion simulation or hydrodynamic simulation. What you see here is the PLM code. And basically what you have here is you have a bunch of cells. And in each cell, you have to solve a small sparse system that is basically reflecting the chemical equations that you have to solve during this combustion process. And what we did is we developed functionality that is specific to that scenario, because the size of these sparse systems is relatively small. It's like 50 or 100, so significantly smaller than what we usually handle with sparse functionality. But using sparse iterative solvers in batch fashion inside Ginkgo gave us a significant speed up over the default option, which was using dense direct solvers, so LAPAC style solvers. And in particular, on this in this setting, we were also significantly faster than the NVIDIA devices. So we were significantly faster on the Ponte Vecchio than on the NVIDIA GPUs. We developed that functionality for the combustion simulation, but then a different community came to us and said, like, hey, we are having a totally different problem. We are doing fusion plasma simulations, but the functionality that you developed, that is exactly the same that we need. So we have relatively small, sparse systems that we want to solve. And inside that plasma simulation, what they did is they had the collision operator. So when electrons and ions collide, and this results in sparse systems of size maybe 1,000. And up to then, they were similar to the combustion simulation. They were using LAPAC functionality on the CPU. And now that we provided that functionality as part of the Ginkgo hardware, they could swap that. They could swap the direct dense solves into the sparse iterative solves. And on all the hardware architectures you see here, Perlmutter, which is an NVIDIA-based system, Frontier, which is an AMD-based system, and Aurora, they could swap the LAPAC-based dense functionality with the sparse iterative solvers from Ginkgo, and they got significantly faster. So that was quite a success. So overall, we developed Ginkgo and now put it into the oneAPI ecosystem as a oneAPI math library. So anyone can use it. Anyone can use that functionality and plug it into their combustion simulation, into their fluid flow simulation, or any other simulation that basically relies on solving linear systems, and therewith can port to any of the Intel GPUs and any of the hardware that is supported by the oneAPI ecosystem. And with that, I thank you and welcome any questions.